Hello, welcome to this session, a session of series and sequencing. We are going to see how best we can differentiate between a sequencing and a series, how we get the partial sum, arithmetic mean, and all that. Now, we've oftentimes asked ourselves what a sequence is. A sequence is a set of numbers, each of which can be obtained by any definite law. If that one happens, then you call that one a sequence. Any set of numbers, irrespective of which numbers, for as long as each of which can be obtained from a definite law, we call it a sequence. However, there are two forms of sequences. We have the arithmetic sequence and the geometric sequence. Remember that the numbers in such a set are called terms. Each number that is comprising of the set of these ones that form a sequence is called a term. Take an example of this. We have the arithmetic and geometric sequences, then arithmetic. Now, in such a set, if someone has a number or a sequence, it may be 1, 3, 5, 7, 9, 11, maybe 13, and this person stops there. Then here somewhere they have 2, 4, 8, 16, 32, say 48, and somebody stops there. When you look at this series, do you remember this next number in the sequence? When you have this, from the first term, if this is the first term, M may be the second term, and this is the third term, fourth term, if you call this one the fifth term, and so on, then you call this one your first term, second term, third term, fourth term, then fifth term, and so on. When you have this, the difference, to get the second term, ask yourself, what did you add on the first term? You realize that you add on a 2. Look at the second comparison. When you look at 5 and 3, what do you add on 3 to get a 5? You find out you add on a 2. In reality, you're going to find out that you're going to go on adding on a 2 to get the next figure. So if that one happens, that is an implication that when you get the second term in this sequence minus the first one, you get it. Third term minus the second, you get the same. Even if you got the sixth term minus the fifth, you end up getting your 2. That's why we call it a common difference. In an arithmetic sequence, from one term to another term, we either add or subtract a constant quantity that we call a common difference, and we denote it by letter D. When you realize you get 9 minus 7, you get up to 5 minus 5, you get up to 5 plus 2, you get 7. That's why I'm saying you either add or subtract. Now look at this. When you look at this, look at the first term, the second term, the third term, fourth term, and all the terms. To get the second term, ask yourself, what is added or multiplied on a 2 to get a 4? You find out that here I multiply the first term by 2 to get the second term. To get the third term, you realize that you multiply the second term by 2 to get the third term. To get the fourth term, you are going to realize that you multiply by 2, the third term by 2 to get the fourth term, so on. If this one happens, just do it in a reverse direction and say, second term divided by the first term, you get 2. The third term divided by the second term, you still get 2. Even if you get the 60th term divided by the 50th term, still you will get a 2. That is why we say in a geometric sequence, we don't have a difference. Rather, we have a common ratio. Common ratio denoted as R. That's what happens. We say a sequence, this set of these numbers. Of course, these numbers can be obtained from any definite law, and we call it a sequence. This is a geometric reason, it has a common ratio. This is arithmetic because it has a common difference. Now look at this. The first term, A, is 1, but the second term is 3. Have you imagined how we go to the second term from the first one? Look at this. This person must have said it is the first term. To get the second term, this person must have said it is A plus. When you get the first term plus the common difference, you end up getting the second term. So it is plus the common difference. When you look at the third term is 5, have you asked yourself how the third term was arrived at? Look at this. If I had made it clear here that the first term A is, then the second term is A plus, the common difference. Then the third term is 5. It is A plus. Now, when you look at this 2, which is the common difference, and you multiply it by 2, you end up getting a 4. 4 plus the first term, you end up getting a 5. And implication that they multiplied twice of the common difference. We are writing these terms in relation with the first term and common difference. When you look at the fourth term, which is 7, is an implication that someone got the first term and added on, first term is 1, to get 7 you add on a 6. How do we get a 6? We multiply the common difference, which is a 2, times 3. In this you're getting the first term. So in reality, if you want to express the arithmetic series in a way that someone can use first term and common difference, it is always written as, let me assume, since the space here is a bit limited, assume this is the third term. So up to the nth term. The nth term, look at this. To get to D, this person has, do you know what this person has done? This is the third term. If it is the third term, now n becomes 3. If n is 3, to get A plus twice D, this 2 would be the number of terms which is 3. So they subtract 1 from n to form a 2 and multiply the common difference. So it applies here. It is A plus, now this is D alone. Reason, this is the second term. You get the second position, which is the value of n minus 1 times D, making it D. So to get the nth term, we get A plus n, which would be 3 now, minus 1 times the common difference. And here someone can vividly conclude that therefore the nth term of an arithmetic sequence is given by A plus n minus 1 into D. Somebody can vividly say this. That is the nth term of an arithmetic sequence. If this one happens, how about the geometric sequence? For the geometric sequence, look at this. From the first term to the second term, you have the first term, which is A. The second term is 4. Our first term is 2. So when you get 2 times the common difference, which is 2, you end up getting the 4. You realize that? An implication that to get in a second term, somebody got the first term times the common ratio. The common ratio is power 1. By the way, even the first term, the common ratio, you have AR power 0. Because the first n here, see this is the first term, n equals 1. So when you say n minus 1, it is 1 minus 1, which is a 0. Any number to power 0 is always 1. So we end up getting a times 1, remaining with only the first term. So to get the third term, which is 8, somebody, are you aware that multiply the second term times to get the third term? If that is the case, it implies somebody got A times the common ratio, which is R, but is square. To get another term, we get to the position, which is n now, and subtract off 1. So to get to the fourth term, it will be A R cubed. Cubed coming in after getting 4 minus 1. And if somebody was asked to write the expression for the nth term of a geometric sequence, would say there are very many terms in between here. AR, because this is the fourth term and we have power 3, it implies that we got 4 minus 1, n minus 1. So we shall have power n minus 1. So therefore, somebody can vividly say that the nth term of a geometric series is given by AR power n minus 1. There is something that we need to see here. If they asked for the arithmetic mean, how do you get it? The arithmetic mean, they mean a figure that is in between the given two values. If they ask you for the arithmetic mean between 1 and 13, they want that figure between this 1 and 13. So you get the first figure that is being asked, plus the last one, you divide everything by 2. This is how you get the arithmetic mean. Take an example here. If you want the arithmetic mean, a figure between 5 and 9, we shall say it is 5 plus 9 divided by 2. 5 plus 9 gives you 14. 14 divided by 2, you get a 7. And a 7 is in between 5 and 9. If they tell you to get the arithmetic mean between of 9 and 13, what you do, you get 9, which is A, plus 13, which is B, divided by 2. 9 plus 13 is 22. 20 divided by 2, end up getting 11. Tomorrow somebody's going to tell you the arithmetic mean between 5 and 11 now. 5 and 11. So just get 5, which is A, plus 11, which is B, divided by 2, giving you 5 plus 11, you get 16. 16 by 2, end up getting an 8. So between 5 and 11, there is an 8 somewhere here, because these two, because there is an 8 between them. So that figure in between the two given values is what they call the arithmetic mean. For arithmetic series, this is how it is done. How about for a geometric series? Sorry, a geometric sequence. A geometric sequence, geometric mean is given by the square root of the two numbers that have been asked, of A times B. Let's assume that you're getting the geometric mean of 8 and 32. You will just say the square root of 8 times 32. When you get 8, it will be 2 root 2 times, when look at 32, when look at 32 practically, it will be 4 root 2. And when 4 multiplies 2, you get 8 times 2. Because root times root 2, you get 2. 8 times 2, you get 16. 8 times 2, you will get 16. You end up getting the 16. A figure in between 8 and 32, end up getting 16. That is how you get a geometric mean for any given pair of numbers asked from you. If they ask you the geometric mean of 2 and 48, it is just fine. You just say it is 2 times 48. After doing that, do the calculation. The square root that you get will define the number that is in between these two values asked from you. Before we head on too much, there is something, someone can ask for a partial sum of an arithmetic series. A partial sum of an arithmetic series, this person is asking you for the sum of all of these values. If you ask maybe the sum from 1, 2, 3, 4 up to the fourth term, how do you get the sum of the fourth term? How do you get the sum of 1, 2, 3, 4, the first term of a geometric series? If it is a sum of an partial sum of an arithmetic sequence, we shall say it is equal to the first term plus the last term. We divide by 2 and multiply it by the number of terms. Now, because space is limited, I'm going to write there. From here, I'm going to the other side. Just to show if they wanted us to get the sum, the partial sum of the first 5 terms of this arithmetic series. They want us to add up to 9. We'll just say practically the sum of the 1, 2, 3, 4, 5 of the first 5 terms of that sequence will be 1 plus 3 plus 5 plus 7, then plus 9. So we shall have 1 plus 3 giving us a 4, 4 plus 5 giving us a 9, 9 plus 7 giving us a 16 plus 9 giving us a 25. How about when we use this simply that? We shall have sum of the first 5 terms. Now look at this clearly. So we shall have A, which is the first term, and that is 1, plus AN, which is the last term, and the last term we say we are doing the first 5, and the last term in this sense is 9. We divide it by 2 times n, and this n stands for the number of terms, which is 5. So we shall have 1 plus 9 giving us 10, divided by 2, 5 times 5 giving us a 25. So instead of facing it rough writing this and adding individual values, it is better to use this. Always ask for the partial sum of an arithmetic sequence. In this sense, somebody can opt to add from the first, second, third, fourth, fifth, sixth, seventh term using this. So somebody will say the sum of these 7 terms would be the first one, which is 1, plus the last one, which is 13, divided by 2 times n, and n is 7. So we shall have 1 plus 13 giving us 14 by 2 giving us 7. 7 by 7 you get 49. So you get 49. And practically if someone added this 13 plus 11 you get 24. 24 plus 9 you get 33. 33 plus 7 you get 40. 40 plus 5 45 plus 3 48 plus 1 49. Practically when you add, you get the same answer. Yet this person who did this has solved it a little simpler. How about if you're looking for the partial sum of a geometric sequence? For a geometric sequence, we get the first term. We multiply it by the difference between 1 and common ratio power n. We divide it by 1 minus the common ratio. When you do this, the answer that you get solved from this from this sequence gives you the partial sum of the geometric sequence. Like I said, the space may not be very adequate. I'm using this for this, and I'm using this for the continuation of this. I hope every person will follow it clearly. Now, assuming someone says, let me get the partial sum of the first 4 terms of the geometric sequence given here. That is 2 plus 4 giving you 6. 6 plus 8 giving you 14. 14 plus 16 giving you just that. Now, here is a person who says the sum as regards to geometric sequencing will be the first term, which is a 2, into 1 minus r, which is 2, power n, and n is now 1, 2, 3, 4. N is 4 because you are stopping at the first term. After that, we divide it by 1 minus r, which is a 2. So we shall have 2 into 1 minus 2 power 4 is 16. So it will be minus 16 divided by negative 1. 1 minus 16, you get negative 15. So we shall have a 2 times negative 15 out of negative 1. The negative cancels out with the negative to form a positive. So 2 times 15 practically gives you a 30, just like someone who added these ones individually. With this, allow me call it a sequencing. We said we have two arithmetic and the geometric sequences. Then we've seen how to get the arithmetic mean, geometric mean, the nth term, then the partial sum, and the partial sum. Now, there is one thing that you need to know still. Sometimes they may give you a sequence of this nature. Maybe the same 1, 3, 5. This sequence, where you don't have the nth term given to you, is called an infinite sequence because it adds up to infinity. Infinite because it adds up to infinity. But look at this one. This one, where you have the first term and the last term, the nth term given to you, is called a finite sequence because it is very well known. We know its start and its end. Where you don't have the nth figure, the nth term, we say that one adds up to infinity and is an infinite series, all sequence in this sense. Hope that is that with a sequence. Now the questions have been arising, I'm very sure. What about a series? What is a series? Hope this is very clear with every person. For the examples about this, maybe we shall do them in another tutorial. Okay. Now, a series. A series is a sum of all the components of a sequence. That's what they call a series. Look at this. If we have 1, 3, 5, 7, and we have 1 plus 3 plus 5 plus 7. This one is a sequencing. And in this sense, since it has a common difference, it is an arithmetic sequencing. This one is a series. And since it has a common difference, it is called an arithmetic series. Hope I'm very clear. So, a sequence is the number, list a set of numbers, each of which can be gotten from any definite law. But a sequence is the sum, a series is the sum of the members or of the numbers that form the set of a sequence. Remember, if this one is given like this, we call it an infinite arithmetic series because this arithmetic series have a D, and it is a series because it is a sum of the members of the sequence. It is infinite because it adds up to infinity. We don't know its end value. This one, had it been this, just we say this one is an arithmetic series and at the same time is finite. Why? Because you know it's end figure. So that's the meaning a series and a sequence. A series is just the sum of all the components of a sequence. Hope I'm very understood. Now, the arithmetic progression. What people like calling it AP. The arithmetic progression. Now, we are talking about series now. An arithmetic progression is a form of series where the next value or the next figure is obtained by adding a constant quantity on the previous figure. If maybe we had 3, maybe 6, 9, 12, 15. When you look at this is a sequence. But if somebody does pa, pa, and goes on putting an addition sign here, this one has become now a series. What makes it arithmetic? Because it has a common difference, which is 3. So, an arithmetic progression is a series where to obtain the next figure, we add a constant quantity. In this sense, it is 3 on the previous number. Is it very clear? To obtain another figure, we go on adding a constant quantity or a constant number on the previous one. Then you say that is an arithmetic progression. The moment you find out that it has a given series has a common difference, always make a conclusion that this is an arithmetic progression. And if it has an infinite direction, that the last figure or the nth term is not given, you conclude and say that one is an infinite arithmetic progression. If it doesn't and it has been given to totality, if you have its last figure given on the first one, then you say this one is a finite arithmetic progression. Hope I'm very clear. Now, if in a set, if a series say we have 5, 8, 11, 14, maybe 17. We have this sequence given us very clear, and someone says, I'm writing this one is a sequence, and I'm writing a series out of it: 5 plus 8 plus 11 plus 14 plus 17. If this is the first term A, and this is the second term, the only difference between an arithmetic sequence and a progression is a sign. But these other things are the same. The nth term is the same that we've seen previously here. The arithmetic meaning is the same that we've seen previously for sequencing. The only difference we are making now, we are making it a series by putting a sign in between these figures, but not a comma. So practically look at this. The first term is A. The second term is, look at this. 5 plus 3, you get 8. So 8 minus 5, you get a 3. The same applies to this. The same applies to this. An implication that if we have the first term, to get the second term, they got the first term plus the common difference. And to get the third term, they got the first term plus twice the common difference to get the third term. To get the fourth term, 1, 2, 3, 4. This is the fourth term now. Somebody got the first term plus 3 times the common difference. Plus the last term in this series is 17. Somebody said the first term, which is 5, plus 4 times the common difference, which is D. So we get 4 times 3, you get 12 plus 5, you end up getting 14. So practically, an arithmetic progression is expressed in this sense. If we need to find out the nth value or the last term of this AP, let me cut this one a little short and end it at that. To get the final figure, so we shall say plus very many items here that we don't know, plus the nth term, which is a plus n minus 1 into b. Why do I say this? It is because wherever we are getting the next term, we subtract 1 from the position. This is the third term, but remember, we have 2d. Why? N, which would be 3, we subtract off 1 to remain with that 1 multiplied by. Practically here, n would be the nth position here. So we subtract 1 from it to maintain the order of everything. And this one is how best you can ever present an arithmetic progression, where A is the first term, D is the common difference, and A plus n minus 1 into D is the nth term. So wherever you are asked to calculate for the nth term of an arithmetic progression, you just say nth term is equal to A plus n minus 1 into D. These ones may almost be given to you in each and every question. I say for examples, we shall see in the next video. Now, here comes the situation. Someone is asking for the sum. How do we get the sum of an AP? The sum of this arithmetic progression. If the sum of the n terms of an AP is A plus D plus A plus 2D, the third term, plus maybe, if I stop there, then plus the nth term, A plus n minus 1 into D. If, suppose the nth term is represented by m. I said I will always choose m whenever given a chance of choosing an unknown. So we shall have Sn, sum of the n terms, A plus D plus A plus 2D plus the nth term. Now the nth term is m. If the nth term is m, let me come here and explain to you. When you have 17, the next to 17, if this is m, to get the next to the nth term, you subtract the common difference. Do you realize? When you subtract 3 from this, you get 14. Do you realize that? So to get this from the last term, you get m minus twice d. Do you realize that to get 17 minus twice d, you get 11. That is 17 minus 6, you get 11. So the same case here. If I want many other terms here, then I will say m minus 2d plus m minus d, then plus m. Then the last 3 terms. The last term is m, the second last is m minus d, an explanation picked from here. Then the second last term, an explanation also picked from here. Hope is understood clearly. So if that is the case, if I call this one maybe my equation 1. So what you do, rearrange this equation and write it in a reverse direction. Write it starting from the last 2 figures now, or the last terms. So what you do, writing equation 1 in a reverse sense. So we shall have Sn giving us, it is m plus m minus d plus m minus 2d plus the many terms that are there, plus a plus 2d plus a plus d plus a. Call that one equation 2. After having the two equations, now we get the sum of these two equations. So we shall have, adding equation 1 plus equation 2, we shall have this plus this, you get twice of Sn. We agree with each other? After doing this, now a plus m, we get a plus m plus, look at this, a plus m, then since this is positive d, you cancel with a negative d. So we remain with a plus m still plus. You now look at this. When you have a plus 2d, then plus m minus 2d, the 2d will cancel that and remain a plus m. So we shall have a plus m still. So we shall have plus the many terms that we don't know there. Up to we have anything term. So plus, finally, get this to this. The 2d will cancel with the 2d. So we shall have a plus m plus. The same applies to this. The d will cancel with the d, remain with a plus m. And lastly, we still also have a plus m or m plus a plus m. Call this one equation 3. So when you look at equation 3, we have n terms that are similar. We have these ones and we have these ones. So they are n terms. If they were, maybe if we are adding them, you would call them a given number, that because you're looking for some of the n terms. Since they are similar n terms, so we shall have sum of the first n terms, which is n into a plus m. We take one of them because they are similar. So this is the same as this, the same as this, the same as the many here, and the same as those ones. So what we do, we take one of them since they are similar, and we multiply by their number, because we are looking at the same similar n terms. So we divide by 2, we divide by a 2. So Sn shall practically be n over 2 into a plus m. But I'm concluding it from here. But remember, our m represents the nth term. Hope you clearly remember that m represents the nth term. So we shall have Sn giving us n out of 2 into a plus, instead of m, now we have a plus n minus 1 into d. So we shall have a plus n minus 1 into d. So we shall have finally n over 2 into a plus a, 2a plus n minus 1 into d. So wherever you're asked to find the sum of the first n terms of an AP, I remember an arithmetic progression, we say it is a series where to obtain the next value or the next term, you add a constant quantity on the previous one. That one is an arithmetic progression. We talk about addition and subtraction only, but not multiplication and division. So wherever you need the sum of the first n terms that you don't know, you just use the formula that n over 2 into bracket 2a, 2 times the first term, plus n minus 1 times the common difference. For this tutorial, for this session, that is that. So for the next session, we are going to see examples related to this. And lastly, we shall do geometric progressions. We shall do proof by induction. So please keep on following. Don't forget to subscribe, like, and share with other people that may need this information. Let's enjoy as we learn. Thank you.